Hello everyone, David Ostrowski here. This is data structures and algorithm analysis. In this recording, I'm going to be addressing graph algorithms again. And in particular, we're going to be examining depth first search. So let's get started. Once again, we're going to have a slight review of the graph definitions. We're going to look at depth for first search of graphs. We'll look at by connected components, depth first search of digraphs, and then strongly connected components. Terminology should be familiar with. The graph has a vertex and edges. Definition: the vertex set is declared as a capital V, and the edge set consists of capital E, which consists of pairs of vertices that are adjacent. With directed and undirected graphs, if the edges have ordered pairs, that would be UV. If it's undirected, it'll be represented with the UV, however, with the curly brackets. Okay, and with the ordered, the directed, you have the arrow going, and it could be directed both ways in that case. Proper graphs and subgraphs. So in a proper graph, you would have no loops and no multi-edges, meaning you'd only have one edge between two given nodes, right? A subgraph G prime, if I made it of G, would be established as the vertex and edge prime, where the vertex prime is a subset of E, and the capital E prime edge is the subset of E between the vertices of E prime. Paths in graphs, so then we have a path P, and it's going through a number of vertices as identified in the graphic, and the edge is labeled sequentially, as are the vertices. So the P is known, the path is known as a sequence of vertices, V0, all the way to V of K, whatever number it might be. So where for I goes through P1 through K, V, J minus 1 is adjacent to V of J. Equivalently, P is a sequence of edges, E sub 1 all the way to E of K, where for each I of 2 through K, each consecutive pair of edges, E of I minus 1, E1, shares a vertex. Simple paths and cycles. Simple path would include no edge or vertices would be repeated, and for the exception of being of V0 equal to VK, right? And a cycle would be a path of V of 0 equal to VK, where the K is greater than 1, and it's indicated by the graph below. A connected undirected graph. Here G is viewed as connected if for every path there's a path between each pair of vertices. Meaning what? For each vertice, I can travel to any of the other vertices defined within the context of that graph, right? So I can go from any vertice, may not be the most efficient or the shortest path, but I can reach it. Okay, so that would be viewed as a connected, undirected graph. And going back here just for a second, right? It's important to specify it undirected, because if it was directed, I may not be able, even if it is connected, if it was a connected directed graph, I may not be able to reach, right? If it's going outbound from a given node and there's no inbound path, then I may not be able to reach. So that's kind of a finer distinction between the two. Connected components of an undirected graph. So else G has greater than or equal to 2 connected components of a maximal connected subgraph. A biconnect component is established as a set of edges where there are at least 2 disjoint paths between each pair of vertices, or is a single edge. Size of a graph. A graph is defined again as a V, comma E, capital V, capital E, where the N is the number of vertices and M is the number of edges. And the graph is just those two numbers added together, okay? So N plus M in this example. 2 ways to represent a graph. We've been through this before, just good to review, right? So representing a graph, we can leverage an adjacency matrix. And this is going to be, for undirected, it is going to be a mirror reflection, as you see here. If it's directed, it wouldn't have that representation. And interestingly, I can omit either the upper right or upper left. I'm going to have the same representation specifically to an undirected graph, right? Because 2 of 1 and 1 to 2 is essentially the same edge. It's indicated by 1. So I could have a more compact representation if that's what I'm going for, right, in terms of supporting the algorithm. I can have an adjacency list representation of a graph here, an adjacency list. And this is indicated as a list type structure. Could be a linked list, could be a array of vertices. Any of these, right, could be leveraged as an adjacency list. Here I have a basic list structure it's pointing out, and it has, in this case, a 2-dimensional aspect. It could be 2-dimensional array for that matter. It may not be the most efficient due to the fact that it's not dynamic, right? But in any case, you could use any of these. But we look at this again as an abstract data type, and each of the adjacency is a list of vertices adjacent to V. So for 1, it goes to 2 and 3. And I can see on the top, right, 1 is connected to 2 and 3. So I have that represented as the list. And from 2, I go from to 1 and 3. That's associated in the list. 3, I go to 1, 2, and 4. Because they're all 3 connected. And then 4 is going to 3. So again, some of the finer points of distinction here is that I have an undirected graph. So the representation is less complicated from that respects. And here I can put together a set of pairwise lists. I can have 1, 2, 1, 3, okay, and that would make the association here by having a list extending to the right of the major column here. I have a more compact representation from that aspect, okay. And for that reason, okay, we have the space cost of big O n plus m, okay. And again, when you look at it as more of a dynamic structure, you're going to be saving costs. And of course, we have similar trade-offs in complexity between the representation and manipulating it, okay. So definition of an undirected tree. A tree here, a T is a graph with a unique simple path between each pair of vertices, and n is equal to the number of vertices, and n minus 1 is the number of edges. Here, the forest exists as a set of trees. So here we make the comparison between the graph and the tree, and at the end of the day, of course, the tree is a restricted graph. So there's no difference between the two, for the exception that a tree has obviously more restrictions. And again, you could It's kind of implied by the representation here, but if we have a binary tree and these other form of trees that we've looked at prior, they definitely put additional restrictions on the graph. But it is important to note from the context of these attributes as a abstract data type, right, that we can leverage the different algorithms between them. And we can do depth first, breadth first search in both a graph, more higher level, generalized abstract version, as well as a tree. And in most cases, for initial representations, a tree actually may be more amenable to having a graphical representation exactly what's going on, right? So here we have a definition of what we refer to as a directed tree. So here a directed tree is viewed as a digraph with distinguished vertex root R such that there is each vertex reachable from R by a unique path. So this is following just visually what we know and understand in the context of our earlier implementations of a tree and how it typically exists. Obviously, the root is going to allow access, especially in the context of a directed tree. It's going to allow access to each of the nodes, and if it's directed, uh, it may exist that some of the nodes, some of the children, are not going to be accessed by other children unless they're higher in the hierarchy of that given tree, right? So an ordered tree, it's a directed tree with siblings ordered. Pre-ordered traversal, here we have a pre-order of a root. We order vertices as pushed on the stack. And we can pre-order the left tree and pre-order a right subtree. So it's interesting to note that we can leverage a stack to implement this. We can also do tree traversals in a recursive fashion. And here there's a lot to be learned, not only about tree traversal, but the relationship between inherently recursive type problems and those that don't have that inherent quality, okay, of lending themselves to recursive implementation. And the stack is the bridge between, because we can simulate any recursion through the leveraging a stack, right? So something to keep in mind as we move forward and you strengthen your understanding and comprehension of how things are operated in the context of a tree. So post-order tree traversal would be the post-order left tree and post-order right tree, and then the root. Okay, so here we have, and I need to go back to follow through the actual transitions, but here I have the post order is going to be B, E, H, D, oh, I'm sorry, B, E, D, H, I, F, C, A. Okay. We can compare that to the pre-order, where I have A, B, C, and then down the path of D to E, and then coming back up, and then F, G, H, and I. So an interesting way to apply this, right, could be viewing pre-order as compared to infix and prefix postfix operations. I can look as a tree as supporting an arithmetic calculation, right? And if I have a pre-order, I have the next closest root associated beforehand, right? So, and I could actually bring up an alternative representation here as an expression. Excuse me, and that might uh, assist the understanding here a little bit. So let me do that. I think once you see this and you draw the association, and I'm sure that you've seen already with prefix infix representation, you can see the associations here. So we draw a little scribble pad here and put it alongside our problem. So so I'm going to mock up the tree as an expression, and I could say plus, and I could say a variable, and at each parent node, I could have an operator, and I'm going to and the reason I put plus plus, it's a one variable operator. Okay, so I might be able to draw the make the association, because typically if I'm going to represent an expression in most cases, and I may have a unary operator, so I'm going to represent that as a unary, I would have a full tree, okay, each parent having 2 children. So now the variables could easily be values, right? So if I look at an infix operation, I would have plus a minus plus e and hi, right? So, and how do I know that, right? Because I know that it makes with the pre-order, I make the closest association to the parent to the next 2 children is being applied, right? So here I apply plus to a and the minus, and the plus would be ahead of it, right? So let's make a comparison between pre-order, in order, and post-order traversal, right? If I have a simple expression, let's say I put in values for a and b, this is infix, right? And here I have, if you're familiar with pre-order traversal, right, in any format or prefix operation, a calculator, right, that you would have the operator before, and it makes the association of the next 2 values. If there is not a given value, as we have in the context of C, I would have a subsequent value, and that's the way I operate. So again, here the star HI is going to make the association, and then that is going to be applied to the plus plus will be applied to E, and then the minus between the 2, and that would then be calculated as the, so I can parenthesize this, right? It even make more sense. Now, parentheses can reestablish your precedence. In this case, I'm just reinforcing it, right, and clarifying it a little bit. So here, if you make the association, and then you can have the idea and draw the association between this and that of the values below. So again, we can go back to this and replace that with the value that's actually B. I'm sorry, not A in the first one. So that would be B. So again, I would have A, B, and the minus would be the C, and then D and E, and D, E, and then F and H, I. Okay, so put that aside and let's draw the comparison between that and the post order, and we can see the difference. And go with my simplified example. Okay, so 1 plus 2 in post order would be 1 and 2. We have the close association. So each value is associated to the closest operator, in this case from the right. And we have the post order left, post order right, and that's we have a similar operation, except it's kind of working in reverse here, right? So in a similar operation with the post order, let's kind of look at it from the perspective of the, and I'm going to do it up here, okay, to so we can still look at our primary and make sure I get it right here. In this case, A is going to be the last value that's being considered, and it is going to be addressing the subtree to the left. The post order left tree that's by the first value, and then the post order right tree. So here I have the um, I'm kind of going from backward here, right? So I want to identify the, so I'm really going to start with, I'll start with and I want to replace this so I have the exact values, right? So I'm going to put in B here, and I'm going to, there, that should have been, yeah, so I'm going to put in B. And the left subtree here is E and D, okay? And then I'm going to go to the depth up from here as by connecting through C and go through F and H, and input H, and then I and F afterward, and then C after that, and then A as you see here. So, and I can replace this, right, with the F in this case is the, and again, hopefully this will give you a different, kind of a different viewpoint on it, or a little more insight. And the D is going to be the plus plus, right? And then make sure you get this right. C is the minus, A is the plus. There we go. So I'm working from the right to the left here. And as I build through from the post-order traversal, right, I take H and I. Let's see here. I, B, E, D. Make sure I get this right. So D is applied to E, and then that in turn is going to be applied between the HIF, right? So that's going to be applied to it as a post order, and then the C is going to be applied after that, and then the A finally. So you can match up the algorithm, and again, think of plus 1, 2 and 1, 2 plus, right? That we always have the closest association. It's working from in reverse. Okay, so you don't want to confuse it too much. But D is closely associated to E, right? Because this is going to be evaluated first, and F is going to be close to H and I, and C is going to be associated to the result of these two subtrees, and A is going to be the subtree of B and A, and which would be the plus. So kind of try to apply an expression and give you a better idea of the operations and how they are applied, right? So spanning tree and a force of a graph. Here T is known as a spanning tree of graph G if T is a directed tree with the same vertex set as G. Here each set of T is a directed version of an edge of G. Spanning force, this includes a forest of spanning trees of connected components of G. Here's a spanning tree of a graph, and I have the root directed down to the child, and then an associated path coming back to the tree edge with these associated with these back edges. Okay. Classification of edges with the spanning tree T. Here, an edge UV of a tree is known as a tree edge. An edge UV of the graph G minus T is identified as a back edge. If U is a descendant or ancestor of V. Otherwise, UV would be known as a cross edge, and this doesn't exist in non-directed depth first search. This slide covers the Tarjan's depth first search algorithm. Here we assume a random access machine RAM computational model, and this addresses algorithm depth first search. Here the input graph G consisting of vertex and edges is represented by the adjacency list, adjacency V for each vertex within the entire set of vertices, so getting identified with the capital V, right? And we go through the algorithm and assign the 0 for all vertices within the set. We do the number, assign 0 to the V, and then we assign the associated value to each of the children. So for all vertices, if the number is equal to 0, then invoke the depth first search. And here you would output the spanning forest defined by the children. Now this can be applied recursively. I read depth first search with the vertice, and n is incremented n plus 1, the number of v assigned to n, and for each u in the adjacency, sets of the vertice do if there's a number u equals 0, then add the u to the children of v and invoke the depth first search on the lowercase u. Here we examine the time cost of the depth first search DFS algorithm on a RAM. Here the input size n is equal to the length of the set of vertices and m assigned to the length of the edges. Here the theorem depth first search takes linear time cost, and that is estimated to be O n plus m. Here the proof addresses can we associate with each edge and vertex a context number of operations. Classification of edges of G via depth first search spanning tree, the edge notation induced by a depth first search tree. Here UV, if UV is the tree edge of T, U to V if U is an ancestor of V, and U bridge to V if UV is a back edge, if UV exists within the graph minus T, with either U going to V or correspondingly with the V directed to U. Here's a classification of edges of graph G via the depth first search spanning tree T. Here are the pre-order numbering vertices by order visited in depth first search. The depth first spanning tree T is identified to the right. Without the back edges. Classification of edges of G via the depth first search spanning tree T continued. So here we note the depth first search tree T of an undirected graph has no cross edges UV where UV are unrelated in T. Verifying the vertices are descendants preordering of a tree. Suppose we preorder a number tree T. Here we let D of V equal the number of descendants of V found in depth first search, and this is defined through the lemma of U as a descendant of V if V is less than or equal to U less than V plus D lowercase v. Testing for proper ancestors through pre-ordering. Here the lemma if U is descendant of V and U of W is back edge such that W is less than V, then W is viewed as a proper ancestor of V. Low values for each vertex V. We define low of V equal to the minimum of V union of W, where V is assigned to W. We can demonstrate this by an induction of the low of V is equal to the minimum of V union with the low of W, with V approaching W union with the W of V approaching W. So it's going to be computed during depth first search in post order. Graph with depth first search numbering of vertices and here the low values are presented in brackets. Bi-connected components. Graph G is bi-connected if either G is a single edge or for each triple of edges UVW, such that for every W avoiding the path from U to V, equivalently for every two disjoint paths from U to V. Here's an example of bi-connected components of graph G. Here, maximal edge subgraphs of G are bi-connected, and the bi-connected components are presented in the right-hand side. Bi-connected components, here they meet at articulation points. The intersection of two bi-connected components consists of, at most, one vertex called an articulation point. Here, 1, 2, and 5 are identified are the articulation points, and these are where whoops, let me go back here. Where the back edge is connected to, right? So I know there's a couple separate terminologies for this. So the associated data paths. Okay, that's going to be demonstrated in this case as the articulation points. Discovery by connected components via articulation points. So if you can find articulation points and can compute by connected components, the algorithm during depth first search, you can use an auxiliary stack to store visited edges. Each time we complete the depth first search of a tree child of an articulation point, then we can pop all the stacked edges currently in stack, and then these are popped off edges to form a bi-connected component. Characterization of an articulation point. Here A is an articulation point if either, number 1, A is a root with greater than or equal to tree children, or number 2, A is not a root but has a tree child V with low V greater than or equal to A. And one can note, right, this is easy to check given the low computation. Proof of characterization of an articulation point. The proof here, the conditions are sufficient since any A avoiding path from V remains in subtree, T of V rooted at V, and this is if V is a child of A, and to show the condition necessary, assume A is an articulation point. So the characterization of an articulation point, the first case, if A is a root and is articulation point, A must have greater than or equal to 2 tree edges to 2 distinct bi-connected components. Second case, if A is not a root, then I consider the graph G minus the set of A, which must have a connected component C consisting of only descendants of A with no back edge from C to an ancestor of V. Hence, A has a tree child V in C and low V greater than or equal to A. I have a proof of characterization of an articulation point continued. I have a case 2 and I have the root. And here the point A is identified as not having the root, and we have no back edges that are going back to it. Computing bi-connected components. Here the theorem is the bi-connected components of G is equal to V and E sets, like computed time, big O length of V plus the length of E sets using a RAM. Proof idea, we can use characterization of bi-connected components via articulation points. Here we identify these articulation points dynamically through depth first search. In addition, we use a secondary stack to store the edges of the bi-connected components as they are visited. Here, when an articulation point is discovered, we pop the edges of the stack off to output a bi-connected component. So the bi-connected components algorithm, first step, you'd initialize the stack to empty. And during a depth first search traversal, add the visited edge to stack, compute the low of the visited vertex using lemma. Test if V is an articulation point. If so, for each U of the children of V in order where the low of U is greater than or equal to V, pop all edges in the stack up to including the tree edge. Here we'd output the popped edges as a bi-connected component of G. Time bounds of bi-connected components algorithm. Here each edge and vertex can be associated with big O1 operations, so the time of the length of V plus E. Depth first search of a connected graph. So here I have a depth first search tree T of a directed graph. G is equal to V and E as usual, right? And I have the associated diagrams here. The pre-order numbers give the order of vertices and are visited first in the depth first search. And the white indicates the first number equal to the order discovered, and then the yellow is the post order to the order vertex popped off the depth first stack. Here the post order numbers give order vertices as are last visited in depth first search. Next is the classification of a directed edge, UV, via the depth first search. Spanning tree T, here the tree edge, UV, with U assigned to V and T. The cycle edge would be if V is associated or descendant of V and T, and V assigned to U. Forward edge, we're checking if UV is within T, but U is assigned to V and T. And cross edge is otherwise UV is not related to T. Topological order of a cyclic directed graphs. Here the digraph G, V of E, is acyclic if it has no cycles at topological order. V, going from V1 to Vn, satisfies the Vi to Vj contained within E, where every I is less than j, right? That's in order. Characterization of a cyclic graph. G is acyclic if there exists no cycle edge. Proof here. Suppose U of V within the edge is a cycle edge, so V would be assigned to U, but we let E from 1 to K be the tree edges from V to U. Then U to V, E1 through EK would be viewed as a cycle. Characterization of an acyclic digraph. Case 2, support G has no cycle edge. Then the order vertices in the post order of depth first search spanning forest. For example, in order vertices are popped off a depth first search stack. This is a reverse topological order of G. So G can have no cycles. So this would give a big O V plus C algorithm for computing topological ordering of an acyclic graph. G comprised of V and E, right? Strong components of a directed graph, a strong components for the maximum set vertices, S of V such that for every U, the excess of V within S, and for every cycle containing U of V, Collapse graph, the G star is derived by collapsing each strong component into a single vertex, where G star is viewed as acyclic. Here, a directed graph, strong components are circled, and the directed graph is G, again, with contained by V and E. Algorithm strong components. Input diagram G, we perform depth first search on G, renumber the vertices by post order of the depth first search of G. Here we let G star be the reverse digraph derived from G by reversing direction of each edge. Next, we perform depth first search on G star starting at the highest and post order of G, numbered vertex, and output resulting depth first search tree of G star as a strongly connected component of G. Here repeat step 3, starting at the highest numbered vertex. Not so for visited half when all vertices are visited. Time bounds of algorithm strong components. Time bounds for each depth first search across time C of the length of the vertices plus edges. So the total time would be 2 times the cost, less than or equal to big O n plus V. So another diagram of the strong components algorithm. This is the example input digraph G, and the post order numbering of G is given in gold. This diagram shows a reverse digraph G star with the post order numbering of G given in gold. So proof of the strong components algorithm. Here the algorithm output is the strong components of G. Here we need to show that these are exactly the vertices in each depth first search, spanning force of reverse graph G star. Suppose V and M are the same strong component and depth first search in G star starts at the component at vertex R and reaches V, then W will also be reached in the depth first search in G star. So V and W are put together in the same spanning tree of G star. Proof continued. Let's suppose VW output in some spanning tree at G star. Let R be the root of that spanning tree of G star. Then there exists paths in G star from R to each of V and W. So there exists paths in G to R from each of V and W. Finally, R is the root of spanning tree of G star containing V and W. So if we suppose there's no path in G from R to V, then since R has a higher order post order than V, then there's no path in G from V to R, and this would exist as a contradiction, right? Therefore, there exists a path in G from R to V, and similar argument gives a path from R to W. So R and W are in a cycle of G and must be in the same strong component. So that would complete the proof. So we're going to stop at this point, and I'm going to, again, we're going to be working into the next chapter, and I'm going to try to bring in some additional content as related to the programming assignment. Thanks for listening. Any questions or issues, feel free to reach out to me. Thanks for listening. Take care. And as usual, feel free to reach out to me. Talk to everyone soon. Okay, thank you.